Welcome to our training series on Intel's next-generation firmware initiative, the Universal Scalable Firmware, USF. For this session we will dive a bit deeper into the Scalable Intel FSP interface. Since the platform orchestration layer uses Intel FSP as its SoC abstraction interface, Scalable Intel FSP is an evolution of the current Intel FSP specification. This overview will discuss what does Intel FSP look like today and how will Intel FSP scale it for tomorrow. What is shown here is the timeline and evolution of the current Intel FSP specification. Since FSP 2.0, the FSP binary module has been using three different firmware volumes for CPU, memory controller, and chipset initialization. It functions as a single binary package. An important note is that since 2016 with the FSP 2.0 version, there is no backward compatibility to the earlier FSP 1.x versions. So what is the next version of Intel FSP? Is that the intersection of FSP 2.4 and Intel FSP next version? So what is included in the Intel FSP? And what do you get when you download it? Okay, so FSP is available for anyone to download, and is intended to be the reference code for initializing Intel silicon platforms, or SoCs. A developer will get several things after downloading the Intel FSP repo. First, developers will get a binary file called a firmware device file, FD file, and it contains multiple FSP modules as firmware volumes. The second item is an integration guide. So what does the developer do with this? Well, depending on what bootloader a developer is using, this will tell them how to integrate the FSP binary with the bootloader of their choice. The FSP image will be included as part of rebuilding the platform system firmware image with the build environment of the bootloader. Oh, by the way, where is the FSP located in a particular flash device? Again, the developer will need to determine where in the flash device to insert the binary FD file as part of the build of the bootloader. That brings us to the third item. Because the FD FSP image needs to go in a location in the flash device, and this location may have different addresses than the original location of the pre-built FSP image included with the FSP package, there is a rebasing tool. This tool will fix up all the locations of the binary FSP image adjusting to the location of its placement in the flash device. The fourth item is the boot setting file, BSF, which is the boot setting file containing metadata information. This metadata can be edited by the developer for different configuration defaults for the updatable product data. So we told you what was in the Intel FSP. So what does it do? It provides Intel silicon initialization, as mentioned previously. And this is where, behind the scenes, the underlying code and interfaces inside the FSP is becoming more scalable and modular. The code inside the FSP is going to initialize the silicon, according to the Intel chipset family BIOS writer's guide. The FSP is also relocatable in the flash device, and has configuration capability for platform customizations. And lastly, it is bootloader agnostic. This slide shows a diagram of how UEFI versus coreboot bootloaders interface with Intel FSP. So on the left, the UEFI bootloader uses Intel FSP as the PEI stage, and on the right, coreboot is showing Intel FSP between the ROM stage and the RAM stage. Both examples would be in the platform orchestration layer and independent of the bootloader, use the same APIs for Intel FSP. These same APIs will be used for the scalable Intel FSP. This slide shows more details on the layout of the FD FSP binary file. This is the current layout of the FSP 2.3 spec showing three firmware volumes. A firmware volume is part of the UEFI spec in the platform initialization, PI, Volume 3 specification. The PI spec Volume 3 will describe the details of the UEFI firmware volume. Shown on the diagram on the right is the FD file image segregated into three sections corresponding to the three firmware volumes. Inside each will be its API, its information header and its configuration data. Shown on the left is the entry point call into the FSP interface. Each entry point is similar to a C function call for each of the different modules in the firmware volumes. The first firmware volume, FSP-T, is the temporary memory init. This is for setting up a temporary stack using the Intel No Eviction Mode, NEM, with certain areas in the processor cache. Second is the FSP-M. This is for system memory initialization. The third is for FSP-S for silicon initialization. So what will be the next versions of FSP? For future research and development, Intel is exploring features for FSP like validation and testing, different runtime interfaces, SMM loading, and direct calls from the reset vector to a 64-bit entry point, etc. So let's take a look at just one firmware volume in the FSP binary image. The diagram on the left shows a pseudo layout of a firmware volume with a firmware volume header and then divided up into different sections showing multiple modules or files. The first file within a FSP firmware volume, shown in the middlemost diagram, must be the FSP info header file. Shown on the right is the FSP info header. The interface layout describes the different offsets into the firmware volume for the different API entry points. Each FSP info header has the exact same layout for each firmware volume. However, if the current firmware volume does not have an entry point to an API described in the interface, then the entry point value will be null or 0. This slide shows an example of the FSP-T firmware volume where the entry point to the temp RAM init function is non-zero and is pointing to a location inside the firmware volume. In addition, all of the FSP firmware volumes have their own configuration data sections and layouts. On that note, there are different interface files, .h files, for the FSP-T, -M and -S firmware volumes. These H files are part of the integration guide from the Intel FSP package download. This figure is directly out of the Intel FSP specification version 2.3, Figure 4. This figure shows the FSP API mode boot flow that a bootloader would follow to initialize an Intel platform's silicon and memory. As described in this figure, the bootloader code would be on the outer sides, left and right, and the FSP code is the figure in the middle where the three firmware volumes are pictured. The bootloader would start at the reset vector, top leftmost flowchart start symbol, and then continue to make calls into the 6 different FSP APIs following the boot flow as described in this figure. Intel FSP is a product released by Intel. One can think of the binary FSP product as a black box, where the binary is created from UEFI PIEDK2 style libraries and modules. Bootloaders can interface with this FSP black box through the integration guides, the UEFI PI headers, the VPD configuration data, and the hobs. So what is the path to a more open, scalable Intel FSP? As shown by the arced arrow on this slide, there are set stepping points for FSP growing more open. One goal is to become more transparent about how the FSP is built. As we saw on a previous slide, the Intel FSP can be downloaded from the web, but for the most part, FSP operates like black box binaries. For USF, there is a POC example using QEMU, and a link to a FSP SDK is provided on this slide. The FSP SDK's goal is to provide an opportunity to show how FSP works and allow the system firmware community a way to propose potential changes. The current version of Intel FSP has pre- and post requirements. Bootloaders using the API mode method for calling into the entry points of the FSP functions will typically use some type of wrapper functions to set up the correct environment for the Intel FSP code. The bootloader must be in 32-bit flat mode. Both the code and data selectors should have 4 GB access range. All interrupts are disabled. All Intel FSP calls return an unsigned 32-bit integer as status, where a return value of 0 is success. The Intel FSP will reserve a region of memory for its own use throughout the operation, and this memory region needs to be reserved by the bootloader and OS. Now let's focus on the return data from FSP functions. As previously mentioned, if a bootloader is using the FSP in API mode, typically there will be wrapper functions to interface with FSP. So the way it works is that the FSP function code will create and build a set of data structures before passing control back to the host bootloader. These data structures comply with the HOBS format. The bootloader, through its wrapper functions, will have options for deciding what data to consume from the FSP code, since some data may be irrelevant to the bootloader. How does the host bootloader know how to interpret the returned HOBS data? Since there is a list of .h interface files that is part of the downloaded Intel FSP packages, the host bootloader will be able to interpret the HOBS data structures. This information is also part of the integration guide for each FSP. An example, a resource descriptor HOB can be used for the system memory map information. So what about the Intel FSP using dispatch mode? The FSP dispatch mode fully conforms to the UEFI PI specification and assumes the bootloader will follow the standard phases of the PI boot flow, progressing from the sec phase, to the PEI phase, to the Dixie or payload, etc. In dispatch mode, FSP-T-M and -S are containers that expose firmware volumes directly to the bootloader. The PEIM in these firmware volumes are executed directly in the context of the PEI environment provided by the bootloader. The figure on the right shows, in dispatch mode, the PPI database, PCD database, and HOB list are shared between the bootloader and the FSP. Another new spec that came out July of 2021 is the Intel FSP measurement and attestation specification. This is a way to add authentication. Because if it's a binary, how do you know it's the genuine FSP? According to NIST, Guideline SP 800-155 requires there be firmware integrity measurements. This means each firmware component needs to ensure that industry best practices are followed. Thus, there is a need for firmware integrity reporting. So to meet this requirement, the Trusted Computing Group, TCG, defined how to provide the reference integrity manifest at manufacturing time, and also how to collect the firmware integrity measurement at system boot time. The Intel FSP is an Intel-delivered binary that is integrated into OEM system firmware. An OEM may get the original source code, modify the FSP, and subsequently create an OEM-specific FSP binary. In some use cases, a third party needs to verify the provenance of the FSP binary. This verification includes supply chain concerns about the authenticity of an FSP during update and manufacturing times. As one mechanism for verification, a third-party attestation service can introspect on the component. The FSP identification is the following process. First, the verifier retrieves the TCG event log and iterates to the correct log entry, which includes vendor ID, the reference manifest QUID, the platform manufacturer string, etc. Second, the verifier gets the corresponding FSP reference integrity manifest, RIM, where the RIM software ID tag matches the TCG log's reference manifest QUID, and then compares the corresponding values from the TCG log to the RIM. The following are summary points for the Scalable Intel FSP. The Scalable Intel FSP is an evolution of the Intel FSP specification. The Intel FSP is the reference code for bootloader's interface for initializing the Intel Silicon Platforms, or SoCs. Intel FSP Next has proof of concepts available in the open source on the GitHub Universal Scalable Firmware website. Intel FSP authentication is accomplished through measurements and attestation to verify the provenance of the FSP binary. This concludes our dive into the USF Scalable Intel FSP interface. For our next session, we will take a look at how to configure the configuration data for the Scalable Intel FSP.